we're going to, I had a few animations. Unfortunately, we're not going to be able to use them. So quick recap, we saw what a Hopfield network was. It was a loopy network where neurons activated other neurons. We also saw that the way the network operated, each neuron tried to align itself to the local field. So if the field was positive, the neuron became positive, otherwise it stayed negative. And this meant that a neuron would flip if its sign was not the same as the sign of the local field. So we also saw that you could define something called the energy of a Hopfield net, which is simply the weighted product of pairs, the sum of the weighted sum of the product of pairs of bits, where the weight was the weight of the edge connecting the bits, plus this additional term, which is the bias term. And the reason we defined this energy term was that this looks like a spin glass, where the first term is the internal energy of a ferromagnetic material, and the second term is the influence of a dielectric material, and the second term was the influence of an external magnetic field. So we also saw how to set it up. You would go through the network, and each neuron is going to try to align itself to the local field. These updates will continue until the energy of the system sort of converges. All of these we saw, right? So the evolutions continue. We also saw this until the energy arrives at a local minimum. So you have an energy contour that's got local minima. If you start off at any point, the network will begin to evolve. The bits will begin to flip, and the whole thing will stop once you arrive at a local minimum. And this, we saw, was a content addressable memory, also called an associative memory. These are terms you might want to remember, if nothing else, because they're interesting and because you might encounter them later in life. This has to do with the fact that now, in order to recall something, you're not using the address of where it is stored. You're using the content, partial content of what was in this memory location to recall it. So you are recalling by association, or you're recalling by content. So it's a content addressable memory, or also called an associative memory. And we saw some examples of how this would work. We have this was the Bugs Bunny. If you just give in a noisy version of the Bugs Bunny picture, it's going to reconstruct the entire picture, clean it up. Or if you give just half of the Chip and Dale picture, it's going to fill up the rest of the image to reconstruct it, provided the network is designed to remember these patterns. And wait. So this was noisy pattern completion over here. You initialize the entire network and let the network evolve. Or this is pattern completion, where you see the bits and let the network evolve. And so the two have two different modes of operation. You have a network, you have a whole bunch of bits. And so in the case of the noisy pattern completion, you would have the network with maybe all of the neurons connected to one another. And you'd set all 5 neurons and let the entire network evolve. And it's going to clean up the energy. In the pattern completion, you know the values of these bits. You just don't know the values of the remaining bits. So you fix the values of the bits that you do know and let the network evolve. And if the rest of the bits are going to keep flipping back and forth till they settle down, and they're going to reconstruct the entire data. Very cool. So we saw how to train a Hopfield network. So here's a random question. Does anybody want to take a shot at answering this question? Do you think we can use backprop to train a Hopfield network? Anyone want to take a guess? Why not?
It's not a DAG, or it's like not even like, there's like no really pattern as to where it starts and where it ends.
Okay, anybody else want to guess? So remember, we said that we can actually think of the Hopfield network as an infinitely deep MLP, correct? So I could just sort of use this Hopfield net. I could open it up and keep repeating this, there was something special about this network. What was special about this network? Anybody remember? No self-connections, and the weights are symmetric, and every layer is the same as every other layer, correct? That's about it. So if I want to train this network, I could actually sort of build this network out yay deep, fix in the target pattern over here, fix in the target pattern over here, try to minimize the divergence, right? And this is a shared parameter network. I could train the weights. So although we are speaking of loopy networks, you can always think of it as a very deep multi-layer perceptron where the depth is undefined because the depth is as far as you need to go for the thing to converge. So we also saw that the Hopfield network can be trained to remember specific target patterns, like the pictures in the previous example. And the way we did it was that if you had some pattern, so let's say you wanted some pattern 1, 0, 0, 1, 1, 0, 1 to be remembered, this was a pattern Y, which would be 1, 0, 1, 1, 0. And so you would say W equals Y, Y transpose, which meant that every edge is going to get a connection weight which is equal to the product of the bits. Now, in principle, you're actually doing Y, Y transpose minus of I because there are no self loops, right? But we can ignore it turns out you can ignore the minus of I. It doesn't really matter the self loops. It turns out that if you had these connections, if we've computed in this manner, would not change the behavior of the network. For a very simple reason, it's just a diagonal loading of the weights matrix. It doesn't really matter when you have loopy networks. But anyway, so we could train the network. This was the Hebbian learning rule. To remember a specific pattern, we just set the weights to be Y, Y transpose. More generally, you want to set the weights to remember specific patterns and to not remember other patterns. Now, so here's what we saw we could do. Using the same rule, I can say I'm going to try to find the weight such that the sum of the energy in the target patterns is minimized. The energy in all of the remaining patterns is maximized. And if you simply use gradient descent to do this, you end up with this formula which looks just like the one that I just saw, that you're iteratively updating the weights with a gradient which is the sum of two terms. The first is simply the average of this product term over all of the patterns that you want to remember. The second is the average of the product terms over all the patterns that you don't want to remember, and you're subtracting the second from the first. This is making sure that the weights will remember whatever you want to remember and also not remember whatever it is you don't want to remember. This was a very simple rule, right? And this, of course, meant that the second term would have to be summed over every possible pattern that you didn't want to remember. And we said, well, you don't really need to learn to not remember all of them. There are some things which are more, you can just focus on some. You just find the values in the energy. And so long as you make sure that the values in the energy there are no values in the energy which are not your target patterns, you're fine. So you let the network evolve. It comes at some local value. You pull up the energy at that point, but you keep pulling down the energy at the target patterns. If you repeat the process, eventually only the target patterns will have low energy because you have sort of gone through and pulled up all of the values. And even this can be computationally expensive because you can have an exponential number of values. So we figured that you really need to just pull up the values close to the patterns that you're trying to remember, because again, you're trying to have a content addressable memory, which means that if you're somewhere very far away, you don't want to be remembering anything particular. It's not important for you to remember something that has been destroyed, where 90% of the information has been destroyed, because you can't even be sure what it is you're trying to remember. You want these energy bowls to be to have nice clear minima, but the bolts need to be only a finite diameter around the points that you're trying to remember. So we said that you can just start off at the points that you're trying to remember, let the energy evolve, come to a local minimum, and just pull up the energy at those points, right? And then we went one step further and said, you don't need to actually let the thing evolve all the way to the bottom. You could just start the network at the points that you want to remember. Let it evolve for a small number of steps. That's going to give you a relatively small bowl around that data point. The number of steps is going to be the diameter of the bowl within which you want the pattern to be memorable. And so the iterative update rule would be that you would initialize the network at some point that you're trying to remember, let it evolve for a few steps, and the update rule is going to be this. The first term is pulling down the energy at the pattern you're trying to remember, and the second term is pulling up the energy at the pattern you arrive at after a few steps. And this, you would expect, gives you the kind of behavior that you want. Now, the math is simple. The concept is simple. The whole thing is there's nothing magical about any of it, right? So there was a problem here. That if you look at the figure to the right, it's not a clear recollection of Bugs Bunny. It's got noises. Why do we have the noise? And we saw the reason for this as well. That if you construct this network to have local minima at the patterns that you're trying to remember, then you're going to have these spurious local minima in the vicinity. These are the noisy patterns. Or you're going to have, instead of having a minimum like so, where this is the pattern you want to remember, you might have a minimum like so, where you're off. Now, this has to be improved by training properly, but a more likely situation is something of this kind, where instead of going all the way to the bottom, you end up stuck somewhere close, which is a slightly noisy version of whatever it is you're trying to remember. So when you have a situation such as this, what is the obvious thing to do? If you let the network evolve, it stops at some point, then you jitter it. And then you let it evolve again, right? And so again, the pattern is going to be in many dimensions, this bowl. So you can imagine that if you jitter it, you go outwards in some direction, from where when you let it continue to evolve, maybe it will come down here, right? So adding a little bit of noise to get it out of these local minima kind of makes sense. But how do we justify this business of adding noise, and what is the process by which we do it? For that, we're going to go back today to our good old thermodynamic system, the spin glass. Now, I'm going to harken back to your Physics 101. All of you have done this. And you'll remember that systems try to settle down at a lowest energy point, right? Everybody tries to remember this. How many of you have heard this term Boltzmann constant? Okay, Maxwell, you. You remember hearing about it. Does anybody remember anything more than that? Random motion, you're getting somewhere there, right? So what happens to the spin glass when it actually, how many of you have heard of absolute zero? What does it mean? There is no kinetic energy, no movement, motion, right? All of these are linked, entropy. So how exactly does a physical system behave? I sort of waved my hand. I said that if I have a field, I have an intrinsic field because of the alignment of all of the dipoles. I have an external field that has been put there maybe by some magnet. And so the total energy at any point is the product of the bit and the field, which is going to be the product of b times x, and the field is the summation jx times x, right? And so this we defined was the total energy of the system. And we said the system would evolve and pause, come to a stop when this hit a local minimum. That made no sense. There's more to it than that. What really happens is something like this. It's not good. There's no. This is a physical system. What is the one situation where a physical system doesn't move anymore? Anyone remember? No part of the system moves. Nothing moves. Absolute zero. That is the only situation where a system doesn't have any more motion. Correct? Nobody has seen absolute zero. It's a theoretical concept. So what happens over here is that the system doesn't really stay in one state. It's going to keep bouncing around. The states are going to keep flipping. And what this means is that as the system evolves, you're going to find a greater preference for low energy state and a lower preference for high energy states. So if you let the system just evolve, it's going to the probability distribution with which it visits the states is going to keep changing in a manner that prefers low energy states. So this is the actual manner in which physical systems will behave. So this takes us to the definition of something called a Helmholtz, what is it called? I had to go and look at the top of the slide, free energy of a system. Now at any configuration, the system has a potential energy. If I set all of these bits in some value, to some value, all of these dipoles, the system has some free potential energy. The system has some probability of being in that state, because remember, the system is constantly just bouncing around, right? Unless it's at absolute zero. So the internal energy of the system, which represents the ability of the capacity of the system to do work, is the expected value of the potential energy of the states. Basically, as it bounces around, what is the average potential energy? That's how much energy the system has that it can give up, that you can use to get something else done, like move your steam engine, right? Now, something else counters the system. Why is it bouncing around? Why is it not staying in one place? It's bouncing around because the temperature is not absolute zero. So at any temperature, there is a probability for each state. And we've all heard this term entropy. You think of entropy in terms of computer science terms, but it actually comes from physics, right? The system doesn't stay in one state. The second law of thermodynamics, the systems are always bouncing around. And so the entropy of the system is given by the standard formula minus P log P. This is the noise in the system that prevents it from staying in one place. It keeps bouncing around. If it stays in one state, the entropy is going to be 0 because P is going to be 1 for a single state and 0 for everything else. But more generally, it's going to have a probability of bouncing around between states. So the actual Helmholtz free energy of the system measures how much useful work you can get out of the system. And so that is the potential energy of the system over here. Again, remember, ES is the energy in any state. P of S is the probability of being in that state. So summation P times E is the expected potential energy of the state, right? And this guy here is how much you give up minus kT times the entropy. That's where the Boltzmann constant comes in. The Boltzmann constant tells you how much the entropy has to be scaled by to tell you how much it influences the work, the amount of work that the system can do. And then here is the interesting bit. If I just have the system at some initial temperature, what happens? The system is going to begin bouncing around between the states randomly. But then it's going to keep changing its configuration, the probability with which it visits the states, even at that temperature. And it's eventually going to settle down at some steady state probability distribution. And what is the steady state probability distribution it's going to settle down at? Systems are lazy. They like to give up energy, right? We know this all the time. This is so. It's going to settle down at a minimum of Ft. And if you actually work out the arithmetic, which is to say you just take the derivative with respect to P, Pt of S, and find the PT of S at which this term becomes a minimum, it's a two-step equation, so you don't even have to work very hard at it. You're going to find that the system settles down when the probability distribution over the states is given by this little formula over here, which is the probability of any state is proportional to the exponent of the negative of the energy state of that state divided by K times T. K is the Boltzmann constant, and T is the absolute temperature in terms of Kelvin, right? So the 1 over Z over here is a normalizing term. It's normalizing because if you just sum up all of the exponents, that's going to be some finite number, but it's not going to be 1. So to make the whole thing become a unity, you have to normalize it. So this is physics. So what happens over here is that the system, this distribution is also called the Gibbs distribution or the Boltzmann distribution. It is the probability distribution over states for a system which is at some temperature. And it's the probability of any state is proportional to the exponent of the negative of the potential energy associated with that state, right? And so the system actually evolves stochastically. At equilibrium, when the system is actually sort of settled to some equilibrium distribution, then it visits the states with some probability distribution. And the probability distribution with which it visits the states is this guy over here. This is the Gibbs distribution. Now, this is the physical process of a spin glass. And the most likely state over here is going to be the lowest energy state, because that's what has the highest probability, right? So this making sense to you guys at some high level at least, right? The math is not complex. It's very easy. And you can sort of go back and tie it up with what you studied in college in your first year if you did take a physics 101, which I did. Anyway, so let's go back to our problem. Let's actually make this Hopfield net a model physical systems a little more closely, right? We want to escape these minima. So instead of just having a deterministic situation where it deterministically keeps going down towards lower and lower energies, let's assume that let's model physics again a little more and associate with every state a probability which is given by the Gibbs distribution. So the probability of any state, we've defined the energy of the state. This is the same energy as before, right? But the probability of any state is going to be proportional to the exponent e raised to minus of the energy of that state. And you can normalize this normalizing term over here. This is the Gibbs distribution. And so we are going to make the probability of any state basically equal to the Gibbs distribution value for that state. Now, how does this happen? So this is actually mimicking the spin glass system. What this means is that if you can design your Hopfield network, the math of your Hopfield network, such that the probability of being in any particular state as this system evolves ends up following the Gibbs distribution, then the Hopfield network actually represents the distribution. It represents a specific variant of it called the Boltzmann distribution. And so this ends up being this is a generative model. You can just initialize the model and let it evolve. And eventually it's going to keep sort of evolving through various states. You could sample it and take measurements. And if you took the measurements, those states that you would get are going to follow the Boltzmann distribution. So this is a generative model for a Boltzmann distribution. And the parameters of the model are the weights of the network itself. And so how do you actually make the network follow the dynamics as specified by a Boltzmann distribution? So you want to create a network which is sort of randomly going through the states where the probability of any state is given by the Boltzmann probability for that state, which is to say the probability of any state is proportional to e raised to minus of the energy for that state. So this is what we really want, right? So how do we do that? To do this, to see how we can get to it, let's consider the probability of two different states. So I have one state of this kind, 0, 0, 1, 1, 0, 0. This is a state, right? That's the configuration of all of the nodes. Then I'm going to call this S minus. And then I'm going to call this S plus, where I've chosen just one bit. All the other bits say, so I'll call these minus 1 and 1. That's the, right? And I'm going to choose this one bit. All the other bits stay the same. So this is minus 1, 1, 1, minus 1, 1, minus 1. But this one bit flips. I'll call this S plus. Okay? What is the probability difference between these two states? So the probability of so if I just consider this one bit, if I fix all of the remaining bits, what is the probability of the remaining bits? That's going to be P of Si not equal to j, that is the jth bit, and the conditional probability of Si as j given Si not equal to j is the probability of this bit given the remaining bits, the standard Bayes rule, right? So let's just look at how this works out. So we have two different state sequences, states. They differ in only one bit. Because they differ in only one bit, if I look at the probabilities of the two states, I can decompose it into using Bayes' rule as the probability for the remaining bits times the conditional probability of that one bit, right? And so if I take the log of these two probabilities and take the difference, then the probabilities for the remaining bits go away because they're common to both terms. So you're basically ending up with the log of the probability of S equals 1 given the remaining bits minus the log of the probability of S equals minus 1 given the remaining bits, right? And this log of the difference is simply, or the difference in the logs is simply the log of the ratio. So you're saying this is the log of the probability of Si equals 1 divided by the log of the probability of Si equals minus 1, which is the same as 1 minus the probability of Si equals 1. Again, nothing fancy, right? Very straightforward. And what is the log of the probability of any state? The log of the probability of any state is simply the negative of the energy at that state, because that's how we define the probability of any state, right? So if I look at log of Ps minus log of Ps prime, where the S and S prime differ in only one bit, that is simply going to be the negative of the energy of S minus the negative of the energy of S prime, which is to say that's the energy of S prime minus the energy of S. And if you work through the mathematics, what happens is the energy, if I'm considering any one bit, then the energy of the configuration is the sum of the energies at all of these bits and the energy of this one bit. If two configurations differ in only one bit, these guys will cancel out in the difference. And you're just left with the energy at one bit. It's 2 times the energy at one bit, right? So you end up, as we saw it last time, this is going to be summation Wij. This is I, these are all j of Yj minus. Because there was a half term, half and half are going to sort of add up, right? So basically, you end up with this interesting thing where you say that the log of the ratio of P of S equals 1 and 1 minus P of S equals 1 is simply the field at that bit. You work out the arithmetic, something interesting happens. It's again, I'm just flying through the math because the math is really very simple. You can just take me on faith, and we're all familiar with the famous logistic probability. We've dealt with it again and again and again. And this is where the logistic probability comes out of. It turns out that you can derive the probability for the logistic regression from the Boltzmann equation, which is kind of crazy. It turns out that the probability that a bit takes the value 1, given all the remaining bits, is simply 1 over 1 plus e raised to minus of this term. Now, is this equation looking familiar to you guys? This is your standard sigmoid, right? This is your softmax, for instance. So what does this really mean? All of this crazy math that we went through, which wasn't really crazy. It's just, I flew through it. But if I'd done it on the board, you'd have seen it easily enough. I don't think it was important enough for you to go through the painful math. The bottom line is important. The bottom line is this. The bottom line is that at each neuron, I can define a field at the neuron, which is the total incoming weighted sum of the neurons plus the bias, right? I can define a logistic over the field, 1 over 1 minus e raised 1 plus e raised to minus z. And the probability that this neuron takes the value 1 at this sample. Remember, going through this sequence is basically iterating through the network, right? You keep updating all the neurons. So the probability that a neuron takes a value 1 at any given iteration is simply given by the logistic at that equation, individually for all of the neurons. So what this means is all I have to do is this. I can set all of my neurons to some initial value, then change each of these guys to a logistic equation, compute the logistic softmax, which is going to give me the probability that the neuron is going to take the value 1. I flip a coin with that probability and sample the neuron. And if I sample that neuron, I'm going to get a new set of values for each of these neurons. Then I repeat the process. So instead of deterministically using a threshold to say I'm going to set it to 1 if the weighted sum of inputs is positive and 0 otherwise, all you're going to do is to say I'm going to take the weighted sum of inputs and I'm going to compute a probability with it by putting it through a logistic. I flip a coin according to that probability. If it turns up heads, I'm going to set the neuron to 1, otherwise I'm going to set it to 0. And if you use this process to go through the network, basically initialize the neurons, cycle through the neurons, and randomly set the neuron to either 1 or 0 according to the probability that you have over there. If you repeat the process and keep going through it, if you take a snapshot at any time and measure all of the bits, that sequence of bits represents a state drawn from a Boltzmann distribution. So the process of generating data from a Boltzmann distribution is really trivially simple. All you do is just sequentially apply logistic, the softmax at each neuron, the logistic equation at each neuron, and sample according to the probability that's specified by the neuron, and keep going through the process, right? So here's the evaluation of a stochastic Hopfield network. You initialize the network with some initial pattern, then you go through all of the neurons in each iteration, and each iteration you're going to compute the field at each neuron. You compute a logistic, you apply a logistic function on the field that gives you a probability. You flip a coin according to that probability. If it comes up 1, you choose a 1. If it comes up 0, you choose a 0. Then keep repeating the process. So after going through all of that rather tedious looking math, you end up with something very simple that you're very familiar with. All that happened was that you replaced the threshold activation with a sigmoid activation. And so here's something else beautiful that falls out of it. If you go back all the way to class 1, we started off with talking about threshold activations. Then we said we can replace the threshold activations with a sigmoid, which is a soft version of a threshold activation. What we were really doing in the process, if you were working with binary patterns, was converting your neural network from something that took hard decisions to something that was computing expectations from a Boltzmann machine. So it was they all sort of go back and link up. I've just gone back all the way back to lecture 2 today, right? So this tells me when to iterate, right? Yes.
What did you mean by flip a coin?
Pardon me?
What did you mean by flip a coin?
Flip a coin, this is, you're drawing a, so you can draw a random number from a binomial distribution, right? That's flipping a coin with the probability of heads equals p. This is.
For each neuron, you flip a coin.
So I'm saying for each neuron, you're going to get a weighted sum of field, summation wij yj from these guys, right? And so you can say p equals 1 over, this is z, 1 over 1 plus e raised to minus z, that's p. And then you can draw a random number, a binary number according to p. Right? That's what I mean by flipping a coin, a biased coin, that's all, right? So basically it's random number generation. Now the thing over here is that because you're sampling at each point, you're getting some field, you're computing a probability, and then you're drawing a random binary number according to that probability. You can keep doing this forever, right? So if you're doing this forever, the state of the system is continuously changing. It never stops. But then I started off saying I want to start off with this, I'm performing content addressable memory, right? Recall. So I started off with half of a Chip and Dale picture. I want to fill in the rest. This is never going to actually give me an absolute picture. It keeps changing all the time, right? So how do I decide when to stop and what is the actual measurement I have? That is easy enough. How do you actually recall a memory? And the way you do it is you let the system evolve. You keep, you start off with the system. You keep evolving the system through time. After it's run a certain number of iterations, then you run several steps, maybe 10 steps, maybe 100 steps. And so you're going to get these 100 vectors. You take the average of all of these vectors or the max of all of these vectors, whatever it is, and that is going to give you the final state. So all of this ends up looking like your regular MLP all over again, if you actually look at what's happening over here. So basically you let the system evolve and let these be the sequence of the final sequence of values, right? So you take the trailing end of the sequence of updates, you find the average of all of these guys. The average is going to be some number between 0 and 1 for every bit. If the number is greater than 0.5, you set it to 1. If it's less than 0.5, you set it to 0. So that actually lets you come up with a specific value. You're basically computing the expected value of the state. So this you can use for both noisy pattern completion and for filling in the data, right? Now, it turns out, again, all of this business was to try to escape noise, that escape those local minima, right? It turns out that these local minima can be quite noisy, can be quite deep. So what this means is that if the local minima is deep, you want to have a high probability of jumping out of the local minimum. Whereas if the local minimum is shallow or a small one, I mean, if you're actually in a bowl, so here are the two different situations that can happen. The energy can actually be in a bowl of this kind. And if you're here, you want to jump out. If you're here, you don't want to jump all the way out here. That would be very foolish, right? So how do you control for the step size? This is where you can go back to physics. You can go back and say, I'm going to use this notion of a temperature. And now, if you look at what the Boltzmann, if you go back to physics, you can say that I'm going to divide the field by a temperature term T, which is what happens in actual physics, right? In physics, we said that when the temperature is absolute 0, what happens? The system never changes. But what state does it actually arrive at when the system never changes? It's going to arrive at the lowest and at the most probable state, and it's going to stay there. So at t equals infinity, 1 over infinity is 0, which means all states are equally likely. You have complete noise. The system there is no structure to the system. This is the white smear that you got immediately after the Big Bang. Then the system begins cooling, right? So if the temperature is 1, this is just your standard, this is the Boltzmann machine that we just saw, where you keep flipping according to the probability of each state, where the probability is the logistic computed at the field. And so this field quantifies the energy difference obtained by flipping a current unit. If the difference is not large, if the field is close to 0, then it doesn't matter whether that bit is 0 or 1, right? So the probability of having 0 and 1 are both going to approach 5 if the field is close to 0. Now, if you increase this temperature parameter, then all of the field values begin to go towards 0, which means the probability of flipping a bit begins to increase. And if the t is 1, then you get the traditional definition of field and energy. And if t is 0, then you're basically, or as t approaches 0, you're blowing up the small differences between field values. So basically, this is going to end up always picking up a probability of 1 if the field is positive, and a probability of 0 if the field is negative, right? That becomes your standard Hopfield network, where this becomes a threshold function. If the field is positive, the output becomes 1. If the field is negative, the output becomes 0, right? So here's what we want to do. We're going to start off, if you end up in a situation like here, you want to have a high probability of changing the state, even if the current state has a very low energy, right? Whereas if you're out here, you don't want to have a high probability of changing the state. You want to stay close to the minimum. So your guess is going to be that in the beginning, so we start with this assumption that minima are big bowls and local noisy minima are small bowls. So if I start off with a high temperature in the beginning, I'm going to keep bouncing around and I'm going to get out of the big bowls. But then as I begin decreasing the temperature, I'm going to become less and less likely to get out of big bowls. And so if I start off with a high temperature and decrease the temperature, even if I start the network at this state, it's going to climb up, and then it's going to, it's going to do this, right? And go up, and then it's going to keep doing this, but the size of these steps is going to keep going down till it actually arrives at the global minimum. So we have this notion of annealing, which is also drawn from physics, where you start off the system at some high state and you keep decreasing the high temperature and you keep decreasing the temperature as the system evolves, just to escape local minimum. Anyway, so we've sort of seen what we can do, right? We can, instead of having a deterministic Hopfield network, we can make it probabilistic. The conversion to a probabilistic system is modeling physics in the network. You can model physics even more by introducing a temperature parameter, which makes it more likely that it's going to go up into higher energy states at high temperatures and less likely to do so at low temperatures. Start the energy at a high temperature and begin cooling it till it actually settles down. And this is the property that spin glasses and pretty much all other physical systems also have. When they initially, so when you anneal a system, what happens? You temper steel, you anneal glass, you anneal materials. You start off at a high energy and then let it cool. And basically what happens is that these are bad situations to be in. This is where the system is going to be fragile. It'll break really easily because if you drop it, dropping it is like giving it an energy jolt, right? Then that's going to sort of go over the hump and it's going to end up in a different state. So you sort of start off with a high temperature and let it cool, and the hope is that when you do that, the system will actually end up in a configuration like this one, where if you drop it and you give it an energy jolt, it's going to come back to exactly the same system. So this is what we do. That's a standard physical process. You can mimic this in a Hopfield network in a computational model, right? And when do you stop? Remember that you can actually define the total energy of any configuration, right? And then you have the probability of any particular configuration. You can stop when this log likelihood is going to, as the system evolves, the log likelihood of the system, which is basically the energy of the system, is going to jitter. And when the energy of the system begins jittering, when the jitter in the energy system of the system sort of decreases and comes down to some low value. So as the system evolves, if this is the energy, this is time, you're going to see something like this. This is where you would stop. Keeps bouncing around, right? So stop running when the average of the log probability of the pattern stops decreasing. That's about it. So it's a very simple stochastic system. Now, this thing where you actually make the bits probabilistic. Take a Hopfield network, make the bits probabilistic, and make the probability distribution follow a Boltzmann distribution. This is called a Boltzmann machine. So if you ever encountered the term Boltzmann machine, that's just a very simple Hopfield network where instead of deterministically choosing to flip a bit or not based on its alignment to the field, you can flip a coin using a logistic function, which is computed on the field. That's a Boltzmann machine, right? So how do we actually train this network? We know how to train a Hopfield network, right? But once I make it a Boltzmann machine, there's this whole business of probability thrown in. So if I'm throwing in probability, how does that change my view of the world? How can I train the network? So what I'm going to do in the next 10 minutes is going to show you a lot of math. And then after 10 minutes, I'm going to tell you the math was not required, that we've already solved this, okay? So let me first show you the useless math. Then we'll go back to what we already remember. Again, I'm not asking you questions because I know you guys are sleepy, but here is the semester's ended, I'm sleepy too. But anyway, here was the probability distribution for probability of any state. It was proportional to e raised to minus of the energy for the state, right? The denominator is just a scaling constant, but the denominator is important. The denominator is the sum over all states of the exponent of the energy for that state, correct? So here's what we've got. The probability of any state is e raised to the energy of that state, now the negative energy of that state, divided by the sum over all states of e raised to the negative energy of that state. This, by state, we mean the bit pattern, the complete set of bits, arrangement of bits for all the neurons in the network. So what we want to do, if I want the network to remember specific patterns, what we want to do is to train the network, set up the weights such that the energy, the probability of the specific bit pattern is maximized, right? That's how you can make sure that when you start off with something, it's going to evolve towards the highest probability state, and the highest probability states must be the patterns that you're trying to remember. So you want to maximize the probability of the patterns that you're trying to remember. So the log probability of any pattern is simply going to be the log of the probability, as we know, right? Which is going to be the log of the negative of the energy is simply the negative of the energy, the first term, right? And then second term was the negative of the log of the denominator, which is simply log of the sum over all states of e raised to the field at the state. So the first equation, there's nothing complex about it. I just sort of wrote out the log probability. And this is what I'm going to average over all of the states that I want to remember, right? Now, what are the states I want to remember? These are the states that I've observed. These are the states I'm presenting to the training network as part of my training process. By state, again, I'm speaking of a bit pattern, right? So this guy here is what I would like to minimize. And again, to minimize this, I can just use gradient descent, right? When I use gradient descent, now what are the parameters I want to learn? I want to learn the wij parameters, right? So I'm going to be computing the derivative with respect to wij. And if you look at this first term, if I take the derivative with respect to any particular wij, all that I'm left with is going to be 1 over n summation over s yi yj. So does this look familiar to any of you guys? This was just the Hebbian learning rule, right? The first term is just the Hebbian learning rule. That's all you're really doing. It's the average of these products of bits over all of the patterns. So I didn't have to write the probabilities out. We saw this in the last class. That second term is a little more ugly. What is this guy here? If I take the derivative of this guy with respect to wij, then what is the second term, right? This is summed. There's a summation inside the log, right? And because I have a summation inside the log, I end up with a pretty nasty equation. And something interesting happens. I have a log of summation over s prime. What do I have? E raised to summation wij si sj, right? So this, if I take the derivative with respect to any particular wij, the first thing that happens is this entire term goes into the denominator as summation over s prime exponent of wij, right? Exponent of summation ij wij, whatever this is, right? And then the numerator ends up with the derivative of the exponent itself. And if I just work this all out, I'm not actually going to work it out. That ends up, I've actually worked it out on the slides, simply because it's very important for me to impress you guys with my math. But I'm not actually going to explain it because the bottom line is very simple. The bottom line is the term to the right over here. So this is the summation over s prime. You look at this term over here. That term is simply is a probability by itself, right? It's exponent divided by the summation of exponents. And so you end up with, that's p of s prime, right? And so if you actually work out the second term, that turns out to be the average, the expected value of the product of the two bits computed over all possible states, right? That's the expected value of, that's basically for every state, I take the product of these two bits, weighted by the probability of the state and sum it all up. That's the expected value of the product of those pair of bits. And so when I put it into my math over here, when I put that into the math over here, the derivative of the first term is simply going to be 1 over n summation of over all of the patterns that I'm trying to remember, right, of the products of pairs of bits. The second one is a summation over all exponential number of patterns, p of s prime i, s prime j. So this is over all in very large number of patterns. I'm writing infinite. So and the difference between these two guys is going to be your derivative, right? But then what is the second term? This second term is going to be summing over an exponentially large number of state sequences. So you don't really want to be doing that, right? But it's an expectation. This is an expectation. And what is a cheap way of computing an expectation? You just sample. You sample a Boltzmann distribution, get these so if you want to compute the expectation of any distribution, you can draw samples from the distribution and take the average, right? So I can replace the second term over here by sampling this guy. It's expected value of SI Sj over all possible values of the state, which means you need to go over all exponential possible combinations, which you cannot do. So you're going to simply do it by sampling. I'm going to draw samples from the distribution, and then once I draw samples from the distribution, I'm going to take the average of this product pair over all samples. But then what does it mean to draw samples from a distribution? To draw samples from a distribution, in our case for the Boltzmann machine, drawing samples from the distribution meant you just went through this whole process, this evolution, and then took snapshots, right? So that's just like running your Boltzmann machine. And so literally, you initialize the network, you let it evolve, and then you draw samples, right? And so that's going to give me the second term, right? So if you actually look at what's happening over here, here's what we got. This, if you look at the final derivative rule, this ends up looking like something we saw in the last class. That first thing over here, this is just the average of the bit pairs, products of pairs of bits, on the samples that on the patterns that you're trying to remember. The second term is where you just let the network run and you draw samples, correct? This is basically what happened when we were doing this earlier figure. Where is this? This guy. This is basically all we were doing, right? The first term represents all of the yellow bits, the patterns that you're trying to remember. The second term, you want to get the products over all of the locations where I've got the other blue arrows, but you can't do them. So you just let the network evolve randomly, pick some points, but then all the rest of the logic comes back, right? Do we want to pick things randomly, or do we just want to pick the values? Clearly, you want to pick the values. Do you want to pick every value, or do you want to pick the values close to a point you're trying to remember? You're better off trying to pick a value close to a point you're trying to remember. Do you want to go all the way down to the value, or are you happy just taking a couple of steps? You're happy taking a couple of steps, right? So all that rigmarole, all the Boltzmann machine logic, it comes back to something that we saw in the last class. All this means is that you have all of these patterns you're trying to remember. The first term is going to be the average for any wij. This is going to be the difference between the derivative is going to be the difference between two terms. The first is summation SI/Sj, and the second is whatever a bunch of samples S prime I, S prime j. And if you are doing a stochastic gradient descent, you're going to start off with one random sample, compute SI/Sj for that sample, for SGD. You draw a random sample, you compute SI/Sj for that sample. Then you let the system evolve for 2 or 3 steps. You can end up with a new state, and that's going to give you some S prime I, S prime j. And this will simply be the derivative that you're going to use to update your network parameter. The only difference between the Boltzmann machine and the Hopfield network was that in the Hopfield network you were deterministically letting the network evolve. Here you flip a coin at each neuron. So there's a lot of math to say that you can do the same thing, right? So far so good. What we saw is that instead of just having a Hopfield network behave deterministically, if you let the network have a certain degree of stochasticity, then by flipping a coin, it ends up doing 2 things. A, it gives you a process called a Boltzmann machine. It gives you a generative model that allows you to sample from a distribution, right? It allows you to escape local minima, but as far as the math is concerned, the math was exactly the same the training process is pretty much exactly the same as in a Hopfield network. The only thing that changed was the manner in which the network evolved. This brings us back to another interesting point. How many patterns can the Hopfield network store? And we saw that the number of patterns a Hopfield network can store is of the order of n, where n is the number of bits, right? So if I want to increase the number of patterns I want to store, I have a Hopfield network with n bits, but I want to store 2n patterns. Or I have I want to store 100 10-bit patterns, right? I know that a Hopfield network with 10 bits can only store 10 10-bit patterns. But if I want to store 100 of them, how can I do it? Can anybody give me a guess? Okay, if I was to give you this problem, I have this machine. It can store 10-bit patterns, but it can store only 10 of them, right? Or it can store n-bit patterns, but it can store only n of them. I want to store 100 10-bit patterns. What would I do? Yes? Pardon me? I can just pad them with junk, right? So if I want to store 10-bit patterns, all I would do is I have these 10-bit patterns, 4, 8, 10. I can store 10 of them if I have 10 neurons. But if I want to store 100 of them, I need 100 neurons, right? So all I'm going to do is pad these with 990 junk bits. Because I don't really care what is stored out there, right? So now I've increased the capacity of my network to store more than 10 bits by adding junk bits. And so here's what that ends up being. You have the visible bits. Those are the bits you're trying to store. Those are the bits you're trying to remember. And then you have the junk bits. Those are what you're calling the hidden bits. They're out there. These are things that you don't really need to remember, right? You don't care what these values are. They're there merely to aid you in storing stuff, right? Nothing else changes. The world has not changed. You can go ahead and still use your Boltzmann machine and everything else. All you did was pad with junk bits. But now this actually gives you some extra leg. Suppose I want to make this pattern more memorable than this pattern. What is the obvious thing to do? I make many clones of this guy with many more junk patterns, right? So now I can begin increasing or decreasing the importance of certain patterns by increasing or decreasing the number of clones that I make of it with junk bits, right? In the limit, I can make as many clones of it. I can just say that the probability of any pattern is going to be proportional to the number of junk patterns that I've added to the right. Make sense? Right? So are all junk patterns equivalent, or are some patterns more memorable than others naturally? Simply because we know that not all patterns are the same, right? So here's what we have. Now we have the new capacity is proportional to n plus k. These are the visible neurons, and those are the hidden neurons, right? And now I want to train the network, right? For a given pattern of visible neurons, there are 2 raised to k possible arrangements of the hidden patterns. Which of these do I choose? Or do I even need to choose? Can I say all of them are likely with different probabilities? I just sort of automatically choose those such that the overall probability of the pattern, including the junk pattern, is higher for more likely patterns. So if you work through the mathematics, here's what it ends up being. This is what I will try to do. Again, skipping all of the math, here's what we will do. I'm actually going to use the same logic that I did before. When we were training networks using just a standard Boltzmann machine, we did 2 things, right? We said for every bit pattern, we started off with a bit pattern, let it evolve for a few steps, and we ended up with some other bit pattern, right? But now we also need to handle these junk bits, these so-called hidden bits. So those junk bits also have weights, correct? those two must also be remembered. So here's what we will do. We're going to, what did I do with my chalk? Have my network which has the patterns I'm trying to remember. This is the bits that I'm trying to remember. Then I have this much larger network whose purpose is to increase the capacity of my net. And now I'm going to fix these bits and let these bits evolve, because I haven't actually decided what these bits are, right? And when I let these bits evolve, I actually end up getting a complete pattern, which is the visible bits and the hidden bit combination, right? And that is the bit, that pattern is what I'm going to present to my training, okay? So that is what I'm going to be using for this first term. This is the extended pattern where I've fixed the visible bits and let the hidden bits evolve. Then I'm going to release the visible bits as well, because I want to go down the entire valley, right? And so when I release the visible bits, I'm going to end up with S prime. Now I'm going to let both sets evolve, and I'm going to get the S prime patterns. Again, you can write a lot of math around this, and in fact, there was an entire, cottage industry of writing math around this very simple concept. But the basic idea is very simple. We know how a Hopfield network operates. To increase the capacity, I'm going to add junk bits. But for any pattern that I'm trying to remember, I need to know what those junk bits are. So I fix the pattern I'm trying to remember. I let the junk bits evolve for a few time steps. And I get my completed pattern, which I will use for the first term in my derivative. Then I let the entire network, including both visible and invisible bits, evolve, and get the second term. And this is what I'm actually going to use in my derivative. So this is your Boltzmann machine. So first and of course, you can do the whole thing many times, right? So Boltzmann machines here are stochastic extensions of Hopfield networks, enables the storage of many more patterns than Hopfield networks are, but also enables you to compute probabilities, because there's always this business. You can go back and look at it as a probability distribution, right? So it enables you to compute the probabilities of patterns and completion of patterns. Now, I'll skip this. You can do this once you train a Boltzmann machine, you can do different kinds of things. You can do exactly the same thing as before, right? You can denoise patterns by just putting the pattern that you want, the noisy version of the pattern in the visible bits, letting the entire thing evolve and reading it off. Or you can complete patterns by putting in the bits that you do know and letting only the unknown bits evolve, and then reading them off. They're going to complete bit patterns, and all the other tricks that follow. Now, a couple of interesting things. So how can I use Boltzmann machines for classification? We've spoken of remembering patterns, right? What does remembering patterns have to do with regression? What does remembering patterns have to do with classification? What does any of this have to do with the problems that we usually solve in life? I mean, it's not like we are going through life performing content addressable memory, right? Guess what? All you're really doing is content addressable memory. Everything you do in life is content addressable memory. How so? Here's how. I have some features. I have a class, correct? So if I have features and a class, I can think of the features and the class as one extended vector, right? And so now, in my patterns that I'm trying to remember, the extension of f and c, that extended vector is the pattern that I'm trying to remember. And now, when I'm trying to find a low energy pattern, you're not going to deterministically get exactly that feature every time you're trying to obtain that class, right? there's going to be some noise around it. That's the variation of the features for the class, right? So the Boltzmann machine can actually be used for classification. All you have to do is to add some bits which encode the class to your features. Use that to store, to train your Boltzmann machine. And later, when you get only the features, and even if the features are noisy, right? You get the features, you plug in the features in the yellow bits, the bits that you know, let the rest of them evolve, and the remaining bits which encode the class should recover the class for you. So the Boltzmann machine is a more generic concept than a content addressable memory, or more generally, content addressable memory is basically everything, right? It's regression, it's classification, it's pretty much anything you ever asked for. If anybody ever asked you what it's useful for, here it is, which is why a Boltzmann machine is so meaningful. And so this, a Boltzmann machine, you can actually think of this as a stochastic extension of standard multi-layer perceptrons, right? Where instead of having a deterministic computation, you let it add a little bit of noise and you repeat the process, and you expect that the whole computation is going to be stochastically more robust. You escape local minima. There's some final issues. See, this whole process of letting the network evolve is expensive, right? So you don't want to actually spend all of this time letting the network evolve every single time. So you want to speed things up. But there's also this other issue. I have this visible neurons. If I have 10 neurons over here and 90 neurons over here, then I've got 10,000 connections. So those are the number of patterns that I have. Those are the number of parameters that I would actually need to remember. That's a large number of parameters, right? And so I would correspondingly have to generate those many samples, have to require that much training data for the whole thing to be learned properly. There was a simpler version of it that people came up with called the restricted Boltzmann machine. And the restricted Boltzmann machine had just one very simple thing, extension, in that within this set, the neurons were not connected to one another. So also within this set, the neurons were not connected to one another. The visible neurons connect only to the hidden neurons. The hidden neurons only connect to the visible neurons. Now the number of parameters goes down dramatically, right? So if I had 10 neurons over here, if I had 10 bits here and 90 bits here, the original setting had 10,000 weights. Now it's going to be 10 times 90, 900 weights. It's a massive difference, right? So the size of the network shrinks dramatically. So visible units only talk to hidden units only talk to visible units. This is what's called a restricted Boltzmann machine, originally proposed by a guy called Smolinski, Paul Smolinski in Hopkins. All the other math stays the same, nothing else changes. This is just an a regular Boltzmann machine. But here's the computation, right? There is no looping anymore. If I fix the visible bits, the hidden bits can be computed only once because the hidden bits don't influence each other. Once I get a sample for the hidden bits, you are done. So it's very cheap. And so when I'm speaking of, something like this is really horrible, right? Something like this is really easy. So training becomes easy. I'm going to anchor the visible bits. I'm going to sample the hidden bits once. And then when I do the free running for the second term in the derivative, here's what I do. I'm going to get the hidden visible bits, sample the hidden bits, fix the hidden bits, sample the visible bits. In principle, I should keep running this for a long time, right? And basically, I want to minimize I want to let this thing converge, right? So basically, training means that the derivative is going to be the product of the visible and hidden bits in the first iteration minus the product of the visible and hidden bits in the final iteration. So if you actually let this evolve and you do the Boltzmann machine properly, that's what it ends up being. But then going back to the same trick that we saw earlier, that it doesn't actually have to evolve all the way to the end. It means you just say, from the visible bits, I compute the hidden bits. From those, I compute the visible bits again, and then I compute the hidden bits again, right? And so the difference between the products at this iteration and this iteration is all you really need to update your parameters. So the restricted Boltzmann machine is a nice simplification of the overall Boltzmann machine concept. And anyway, so sort of ran to the end of this topic. RBMs, as we saw, are a stochastic Boltzmann machines, are a stochastic extension of Hopfield networks, right? A restricted Boltzmann machine, again, we saw that a Boltzmann machine can be viewed as an MLP of this kind, right? The restricted Boltzmann machine is a simplification of the whole process in the sense that these are the visible units, hidden units, visible units, hidden units. They alternate. You don't have self-connections over here. And so the entire set, because the sizes of these layers keep changing, the visible units might be 10, the hidden units might be 90. The number of parameters decreases dramatically, the amount of computation goes down a whole lot. So the real benefit over here is the stochastic nature of the model, because the stochastic nature of the model actually helps the system escape minima even during inference. What people did for a long time was to use the Boltzmann machine formulation to train the initial layers of the network, train the network initially, and then use that, start from that point to run standard backprop. And it turns out that that actually makes complicated networks converge, whereas when you have, particularly when you have very little training data, whereas they traditionally wouldn't, right? The extensions like continuous valued Boltzmann machines, and instead of having this thing be the same weight over and over again, you can say that I have a sequence of 10 weights, and then the entire block repeats, and then the entire block repeats, and then the entire block repeats. So you can have different structures that give you different kinds of machines. Anyway, yeah.
Through the class, we assume that the beats are binary. So how do we extend in the case where the beats are continuous?
So that's the continuous valued Boltzmann machine. Basically, what they do is right here. I skipped over it, right? For the visible units, they attach a Gaussian to each unit, which basically, but it turns out it's exactly the same thing, right? If you've the math is kind of ugly. They like to have probabilistic interpretations, call it Laplacians and exponentials. All it really means is that in your standard MLP, anytime you compute some value, you throw in a probability, you're going to get the math, right? Post on Slack. We're out of time on Piazza, and I'll answer these, right? We're sort of to the end of this course. I've glossed over Boltzmann machines because I thought Hopfield networks are more interesting. If you understand them, you can pretty much build up everything else. We haven't gone through a great lot of topics in the course because it's already packed. We would have liked to have some more time to spend on things like the latest architectures, neural Turing machines, what is NTMs, on graph neural networks, extensions to generative models, things like transformers and so on. I recommend that you actually go and read up on these topics. You should be in a pretty good position at this point to understand most of the literature out there because it'll make sense to you. You should also be in a pretty good position to download maybe open source code, the code that people have put out after writing papers, run them and know what's going on, and maybe run it yourself. So this is just your starting point. We've spent 3 months. Hopefully we've ramped up a lot. If you were where I was when I began teaching this course, and you are where I am when I ended the course, you made a lot of progress. And with some luck, it makes a difference for you, right? Thank you.